Hello everyone, I'm Dhara Kansara. I will discuss types of shift resistors in this video and I will cover the following contents: classifications of shift resistors and then serial transfer. In my previous video, I have already discussed about the flip-flop. Flip-flop will store 1 bit data at a time. So if you want more number of data to be stored at a time, then we will use resistor. A resistor is a device which is used for storing the data, and flip-flops will be used to design this resistors. Now, what is the shift resistors? Shift resistors is nothing but a simple resistor which will shift the data right side or left side. Simply, it will shift the data. So shift resistors are nothing but the simple resistors, and resistor contains different flip-flops. Suppose I am going to use 4-bit resistor, then in that resistor we are using 4 flip-flops. Means number of flip-flops is equal to number of bits used in the resistor structure. A set of flip-flops is nothing but a resistor used to store number of data bits. The inputs as well as outputs of a resistor are serial, otherwise parallel, depending on the requirement. It is a sequential circuit mainly used to store the data and moves it to the output on each clock cycle. Now you can see here the classifications of the shift resistors that are serial in, serial out CISO, serial in, parallel out CPO, parallel in, serial out PISO, and the last, that is parallel in, parallel out PIPO. Now in CISO, as its name suggests, serial in, serial out. So this figure shows shift resistor and 4 block shows the bits, number of bits. As I told you, number of bits is equal to number of flip-flops. So you can assume here, these are 4 flip-flops. Okay. Now, you can see here serial in, serial out means data will be loaded serially and will take data serially. At the output terminal, we can take data serially. So this is very slow in process because 1 bit will transmit it at a time. Now next, serial in, parallel out. In this resistor, data can be loaded serially, but will take data at the output terminal parallelly. Means simultaneously at the same time we can take data at the output terminal. So this is quite fast compared to CISO. Now parallel in, serial out. The data can be loaded simultaneously but can be removed only as 1 bit at a time for each clock pulse. In this resistor PIPO, last type, that is PIPO, the data can be loaded and read out into the resistor simultaneously. There is also a bidirectional shift resistor of this type where the inputs can be shifted right to left or left to right. So data will be taken simultaneously. So this is fast compared to another 3 types. Now we will see all these resistors, shift resistors in detail. First is CISO. This is the diagram of 3-bit serial in, serial out shift resistors. As I told you, number of bits used in serial resistors is nothing but number of bits is equal to number of flip-flops. Here I am using 3-bit CISO, so I will use 3 flip-flops in the circuit. Here I am using D flip-flop. You can use any type, JK or T type flip-flop. Here we are applying input, serial input to this D input, output taken from this Q2. This output will be input to the next flip-flop, that is D1. Then output of this Q1 will be given to D0, next flip-flop. And here Q0, at Q0 we are taking output. Means at a time, 1 bit data will shift to right side from D2 to D1, from D1 to D0. See, so serial in, serial out. Here you can see clock applying to all the flip-flops simultaneously. Now, we will see this diagram so you can easily understand the working of the shift register. Here, this diagram shows 8-bit shift register. 8-bit means 8 flip-flops we are using. Now data is moving to right side. Here we are applying clock simultaneously to each and every flip-flops. This is what serial data in. I will give this data serially to this first flip-flop. Then this data, this bit, 1 bit will shift to the next flip-flop whenever I will give the clock. So clock we are applying simultaneously, data will be shifted serially. As you can see here, suppose the data right now, suppose 1, then I will press the clock again, 0, then 1. So you can see here 1, 0, 1 will shift right side. Okay, so you can give data from this serial input and apply the clock pulse and data will move. You can see here this data shifting to right side. So this is what serial in, serial out. Now next step, that is parallel in, serial out. This is the diagram of parallel in, serial out. As I told you, suppose I am using 3-bit PSO, then I will use 3 flip-flops. So this is what 3 flip-flops that are of D type. Now, in this circuit, you can see we are using this different logic circuit between these flip-flops. Why? Because there are 2 modes we are using in this PSO that modes are, first, we will load data parallelly to this flip-flop and then we'll shift this data. Okay. So by using this one circuit, we will load the data first and then we'll shift the data to right side. So for that, we will use this signal, control signal, that is shift load signal. Here you can see shift or load bar. Why it is given load bar? Suppose I want to load the data, then I will give this signal. I will give here logic 0. So 0 bar, 0 dash is equal to 1. This signal, so here we will get 1. Okay, load bar, that is I am using inverter here. So this becomes 1 here. So 1 will be given to this AND gate. Now this is what DA, DB, DC. So suppose I want to load the data. At that time, as I told you, this input is 1. And here I am applying DA, DB, DC simultaneously. Suppose this DA is 1 and this signal is also 1. So output of this AND operation will be 1. So here in the lower AND gate, we are applying 0 because this shift signal we are applying to this AND gate. So this is what? 0. So input to this OR gate will be 1, 0. Output will be 1. You know the OR logic, 1 plus 0 will be 1. So this 1 I am applying to this D flip-flop. I have loaded the data here. Simultaneously, I will give the DB. Simultaneously, I will give the DC. So I have loaded this data parallelly, simultaneously. Now, suppose I want to shift this data, then lower AND gate will active, because as you can see here in this figure, I will give shift is equal to 1. So you can see here, this signal I have connected here to lower AND gate. Now this control SI will control this shifting operation. So now suppose I want to shift this data, so output of this will be 1. This 1 will be given to this OR logic. According to, we will get output 1 here. So D is equal to 1. So Q is equal to 1. Now this 1 is given to this AND gate. Now output of this OR gate will be 1. This output will be given to this D input. So like this way, data is shifting to right side. And at this point, SO, serial out, we are getting output serially. Parallelly, we are loaded the data and will shift the data serially towards the right side. Fine. Now we'll see SIPO, serial in parallel out. You can see this diagram. I'm using here 4-bit SIPO. That's why we are using 4 flip-flop. Serial in means you can see here, I'm applying data here to this flip-flop. I'm giving clock simultaneously to all this flip-flop. Initially, we will give this signal, clear signal. What is the function of clear signal? It will clear all this flip-flop. Means initially we can start from 0, 0, 0, 0. So here, this input serial data in given to first flip-flop, that is D. Suppose I'm applying 1 at a time, right? Bit 1, input 1. So this 1 will shift to here. I mean, Q will be 1. So this Q will be given to the input of the next flip-flop. Output of this flip-flop will be 1. This 1 is given to flip-flop 3. And it is given, this output will be given to next flip-flop. Like this way, we are shifting data towards right side serially. But you can see here, at the same time, whenever this data is shifting, at the same time, we are collecting this data to each and every output terminals of the flip-flop. Q1, Q2, Q3, Q4. So we are taking output simultaneously. That's why name is serial in parallel out. You can see here the data as I'm applying this clock, right? So suppose you can use negative edge trigger, positive edge trigger, high logic, low logic, clock pulse. So whenever I will give this clock, data will be shifted serially. You can see here, see Q1 is 1, then Q2 is 1, Q3 is 1, then Q4 is 1. Data is shifting serially. But simultaneously, we are taking output simultaneously. Okay, so this is what SIPO. Now we'll see PIPO, parallel in, parallel out. 4-bit PIPO. So 4 flip-flops are used here. Now you can see parallel data inputs. I am applying data simultaneously and we are taking output, okay, simultaneously from each and every flip-flops. So this is what parallel in, parallel out. Now we'll see serial transfer into resistor. You can use more number of resistors, but we will see serial transfer function with 2 shift resistor. So as shown in figure, we are using shift resistor A as well as shift resistor B. Suppose I want to shift the data from resistor A to resistor B. So how can it possible? Here we are using AND operation and logic. If this shift control is high, Means if we want to shift the data right side, then what happened? This will be high. If this will be high and we are applying clock here, so this output will be high. So now this clock will be given to this resistors. So whenever clock is changing its state from low to high or high to low, the shift resistor will shift the data. We have already discussed different patterns of clock. So suppose I am using high level clock, then at high logic, this shift resistor will shift the data. Now suppose this is, say, shift resistor A with 4 bits, and this shift resistor B contains also 4 bits. Now this is what SIA, SOA. SIA means serial input and SO means serial output of resistor A. This is what this SOA I am applying to shift resistor B. That is nothing but it also known as SIB, serial input of B. And this SOA I am applying to SIA again. This is what? Feedback. And the output of this resistor, that is shift resistor B, is SOB, serial out. This is what clock signal. As I told you, we will give the clock. Means in the 4-bit resistor, suppose I want to store the 4-bit data, then I will use 4 clock pulse. Then after 5th clock pulse, data will be changed. Okay. So suppose we'll take one example. Suppose I want to store data 1011 to resistor B. We will refer this table for this operation. Now, initial value, as I told you, I want to store this data to resistor B. But initially in this resistor, data stored is 0010. But I want to store this data 1011. Okay, so suppose this control signal is on, then now shift operation will start. Okay, so what happened at first clock pulse? This 1 will transmit here, and all this data will shift towards right side. You can see here, first of all, this 0 will removed, and this 1 is shifted to right side, then the 0, then 0, then this 1 will shift here. So at first clock pulse, after T1 means after this clock pulse. Okay, after this clock pulse, data stored in the resistor B like this way. Fine. Here also in shift resistor A, data will shift. But what we are doing actually, you can refer this figure. What we are doing here, we are shifting this data to resistor B. Okay. Similarly, at the same time, we will give this feedback again to shift resistor A. Means suppose we are shifting this data. Okay, so now this 1 is going to next resistor B, but we are applying this 1 feedback to resistor A. Okay, so now this 1 will shift here. This rightmost bit will shift here again as MSB bit. So this 1 is shifting here, this 0 is shifting here, this 1 is shifting here, and this rightmost bit works as MSB bit. Fine. Similarly, at the second clock pulse, this 1 will discard, then this 0 will shift here, 0 will shift here, this 1 will shift to the right side, I mean it will shift here, then this 1 will shift here, but I will give this 1 again to shift resistor A. That's why 1, 1, 1, 0. Now at third clock pulse, again data will shift out, and here it becomes 0, 1, 1, 0, 1, 1, 0. Now at fourth clock pulse, what happened? This 1, 1, 0, 1. Then 1, 1, 0. Again this 1 we are applying back to A. So it becomes 1, 0, 1, 1, 1, 0, 1, 1. So what we are doing actually, this 1011 I want to store in this register B. So after fourth clock pulse 1011 will be here, and shift register A data will not change. So this is what serial transfer. Serial transfer, as I told you, it will transfer one bit at a time. In parallel transfer, will transfer all the bits parallel. Okay, everyone. In my next video, I will discuss universal shift register and application of shift register. Okay, thank you.